Okay, today we're going to talk about independent and dependent events and what is meant by two events being independent. Let's start with an example which is similar to one that you've done before. We have a box with 4 white marbles and 3 red marbles. And we're going to draw 2 marbles, but we are going to replace the first before drawing the second. This is important. Okay, let's draw a tree. So, first draw we can either get white or red. Second draw we can either get white or red, W2 and R2. Okay, so on the very first draw, what's the probability of getting a white marble? There's 7, 4 of them are white, so 4 sevenths, 3 sevenths for getting a red. Okay, so now let's assume that we got a white on the first draw. What's going to happen when we do the second draw? Well, we're going to remove a white, but then what are we going to do? We're going to put it right back in. So we're going to remove the white marble, but then we're going to put it right back in. So nothing changed. So what's our probability of getting a white? 4 sevenths, red, 3 sevenths. Same thing if we drew a red the first time. We're going to put it right back in, so the composition of our box will remain exactly as it was before. So we get 4 sevenths for the white and 3 sevenths for the red. So now we want the probability of getting a red marble on the second draw. So P of R2. So we want to figure out all the routes that can lead us to R2. So here is one way to get to R2. Here is another way to get to R2. And so we multiply along the tree and add them together. We get 4 sevenths times 3 sevenths plus 3 sevenths times 3 sevenths, which is 12 49ths plus 9 49ths, 21 over 49, and we simplify, we end up with 3 sevenths. Okay, now let's look at the probability of drawing a red marble on the second draw, given that a red was drawn on the first. So that means we want the probability of R2 given R1. Well, where is that? Sorry, this should say drawn with an N. R2 given R1, so where is that on our tree? We know R1 happened for sure, so that brings us down here. And we want the probability of getting R2. It's going to be 3 sevenths from here, because we know that R1 happened for sure, so we're already here. We're ignoring the rest of the tree, and we're just looking at this. So we get 3 sevenths. And so, because those two are the same, that tells us that these events are independent. Okay. The outcome of the first draw does not affect the outcome of the second. And that's because we replaced the marble after we drew it. Okay. what we've just actually done is checked that R2 given R1 is equal to R2. Okay, and because this is true, our events are independent. Now let's get to our definition of independence. Okay, independent if the outcome of one does not affect the outcome of the other. If that doesn't happen, then they're said to be independent. Two ways to check this. One is to actually three ways, but two are essentially the same. Probability of A given B is equal to the probability of A. Probability of B given A is equal to probability of B. In other words, whether in this case A is given. So A being given does not at all change whether B occurs, the probability of B occurring. In the very top test, the B occurring, being given, which is what follows the vertical line, does not affect the probability of A occurring. And there's a third test which can actually be created from the first two, and that is that the probability of the intersection of A and B is equal to the product of the probabilities A and B. If we look at our conditional probability definition, which we've seen before, what that says is that the probability of A given B is equal to the probability of the intersection divided by the probability of the given. So in this case, B. Now, if they're independent, then the probability of A given B is equal to the probability of A. So I'm going to replace the left-hand side with the probability of A, because if they're independent, these are the same. So I can call that P of A, and so now my equation looks like this. P of A is equal to the probability of the intersection divided by the probability of B. And now if I multiply both sides by that denominator to clear out my fractions, then I end up with probability of A, probability of B is equal to probability of the intersection. That's our third test for conditional probability. Independence of events using the conditional probability formula. And it turns out this is often easier to use than the first two, even though the first two may perhaps be more intuitive. Let's do an example where we test whether events are independent or not. Okay, so let's draw a single card from a standard deck at random, and we're going to test a couple pairs of events for independence. Okay, so let's look at this first one. Let's let H be the event that we draw a heart, and let's let F be the event that we draw a face card. And those will be our kings, queens, jacks, the ones with faces on them. Okay. And how many face cards are there? There are 3 in each suit times 4 suits, so 12. Okay, if we're going to use that third test, we need to test whether the product of the probability of the intersection of these events is equal to the product of their probabilities. In other words, if I take the probabilities of the two individual ones and multiply them together, is that equal to the probability of the intersection? So that means there are 3 probabilities that we need to find here. The probability of H We know there's 13 hearts, 52 cards, so 13 out of 52 are a fourth. The probability of getting a face card, there's 12 of those out of 52 cards, so 3 over 13. And so therefore the probability of H multiplied by the probability of F is equal to 1/4 times 3/13, which is 3 over 52. Okay, now H intersect F is going to be what? Let's just describe it. Okay, it has to be a heart and also a face card. So that means it might be the King of Hearts, it might be the Queen of Hearts, it could be the Jack of Hearts. There's 3 of those, so the probability of that intersection then is going to be 3 over 52. So what are we comparing? These two. Okay, and so each of these turned out to be 3 over 52. So that means our condition for independent events is satisfied. So drawing a heart and drawing a face card are independent. Now, let's look at the probability of drawing a king and drawing a queen. And before we start, just pause a second and ask yourself, would you expect these to be independent? Just kind of make a mental note of your answer, and then let's move on and test it, and we'll see if you were right. Okay, so here we're going to let K represent drawing a king. We're going to let Q represent the event that we draw a queen. And so we want to test whether the probability of king times the probability of Q is equal to the probability of K intersect Q. Okay, well, what's P of getting a king? Well, there's 4 kings, 52 cards, or so 1 and 13. Queens, same thing. Okay, so we've got those, and then we can even go ahead and multiply them together. So that'll be 1 over 13 times 1 over 13, which is 1 over 169. Okay, so now we need to look at the intersection. Okay, so what is in the intersection of kings and queens? In other words, what cards can you list that are a king and also a queen? I hope you said none. King intersect queen, K intersect Q as we have them defined here is empty. We cannot have a card that is a king and is also a queen. Remember that intersection means and. They both have to be true in order for it to be in the intersection. So it's empty. So what is the probability of that happening? 0. So is that equal to the 1 over 169? Certainly not. Okay, these are definitely not the same. So we call these dependent events. The outcome of one does affect the other. Now, if you were one of the many people who, when they first look at this problem, think, yes, those should be independent events, let's check back with our intuition. Apparently our intuition was wrong, so let's see why that would be true and see if we can make this jive with logic. If you phrase the problem another way, remember that being independent means the outcome of one does not affect the other. So, if you drew a card and you already knew that it was a king, and then someone asks you, what's the probability of this card being a queen? What would you say? Well, 0. You already know it's a king. In other words, the fact that it's a king certainly affects the probability that it's a queen. Therefore, those two events are not independent. The outcome of one does indeed affect the other. These are dependent events. Okay, let's do another one that's a useful example that we'll often find when we do surveys and statistics. Let's suppose we have a group of 2,000 women, 680 smoke heavily, and 50 have emphysema. 42 of the emphysema sufferers are also heavy smokers, and we want to determine whether being a heavy smoker and having emphysema are independent events. So let's let H be the person selected is a heavy smoker. And let's let E be the event that the person selected has emphysema. And we want to determine whether H and E are independent. So what we need to do is we need to test whether the probability of H times the probability of E is equal to the probability of the intersection. Okay, you can also use one of the other two tests for independence. I think most people are more comfortable with this one. The probabilities are not difficult to calculate. So P of H is going to be, okay, how many heavy smokers do we have here? 680 of our 2,000 in our sample. So that gives me 0.34 for a probability. The probability of E, there's 50 people with emphysema, so 50 out of 2,000. So that gives me a probability of 0.025. Let's multiply these together. .34 times 0.025, and that will give us 0.0085. Now we need to figure out the probability of the intersection. So how many people in this group fell both into the heavy smoker group and also the emphysema group? Let's see, which people would that be? That would be these 42 people, right? They have emphysema and they're also heavy smokers. And so we have 42 of our 2,000 that fall into the intersection. That gives me a probability of 0.021. Okay, so these are the two numbers that I want to compare. Okay. So we're going to compare these. Do they match? No, they don't. And so that tells me that these events are not independent. In other words, they are dependent events. And sometimes we just say not independent. Now, our definition, actually our test for independence, can be extended to more than two events. Here we had two events, so we multiplied the two probabilities together compared with the intersection of the two probabilities. But we can actually do this when we have more, however many events that we want. If we have a whole bunch of independent events, n of them, the probability of the intersection of all of those will be equal to the product of all the probabilities. And so this is often useful you can use this as a test for independence, but you can also use it as a calculation. If you know that events are independent, their outcomes are unrelated, then you can use this formula to calculate the probability of a whole bunch of them occurring at once. So here, let's suppose we have a loudspeaker system with 4 components: woofer, mid-range, tweeter, crossover. And we know a percentage of each of those components that is defective. And we want to figure out the probability that a randomly chosen loudspeaker system is not defective. And here, this is very important, we're going to assume that the defects in the different types of components are unrelated. In other words, these components were made separately, so a defect on one does not affect whether another one is defective, but then we just put them all together into a system. So what we need to do here is define some events. If I let W be the event that the woofer is good or non-defective, you could work with the woofer being good or the woofer being bad here. I think it turns out to be easier to do it this way, to just define our events to be that the component is good rather than bad, and that saves us having to do complements, or at least to write down complements. So M will represent that our mid-range is good, and T that our tweeter is good, and C that our crossover is good. Okay, now let's figure out the probabilities of each of these. The probability that the woofer is good, well, it hasn't given us that, but it's told us how many of the woofers are defective, 1%, so we convert that to a decimal, subtract it from 1 to figure out the probability that it's good. So that puts us at 0.99. 1% are bad, therefore 99% are good. Do the same thing for the mid-ranges. 1 minus, careful with your decimal places, 0.08 would be 8%. We want 0.008. And so that gives me 0.992. The probability of our tweeter being good, we subtract 0.005 because 0.5% are bad. So we get 0.995. And for the crossovers, 1 minus 0.015, so that gives me 0.985. Okay, so now I have probabilities that all of these are good. So in order for my loudspeaker system to be good, then, I need all of these events to happen. It means it has to have a good woofer, and also a good mid-range, and, remember intersection means and, a good tweeter, and a good electrical crossover. So according to our fact about independent events right here, we know that this intersection ought to be equal to the product of the probabilities of the individual events. So we can just multiply all these together. 0.99, 0.992, 0.995, 0.985. Multiply all these together, and you should get, and this is an approximation, 0.9625. And again, as always, ask yourself, is that reasonable? We certainly should expect that most of the time our loudspeaker system should be fine. The bad parts should be fairly unusual, and it looks like we have about 96% of the time our loudspeaker system is good. And so here's another way in which the fact that these events are independent helps us to do a calculation. Well, I hope this helped you to understand independent events. See you next time. Good luck.